Okay, here we go. I'm going to go through this kind of quickly because I want to get the video up because the video that was up there apparently didn't have any sound. So it's too bad that I have to do this alone because this is kind of a neat lesson where we talk about some interesting things, but I'll speed it up a little bit and we'll get to the actual doing of the question. I quickly want to talk about this demo that we looked at on the first day of this unit, and it's neat that it comes full circle and we're talking about it again. We talked about Ferris wheels, and we talked about that because you intuitively know things about Ferris wheels. Everybody's seen a Ferris wheel, understands what one is, and we talked about the things that make a Ferris wheel important, the things that make one different from another. And we said it was things like the height of the Ferris wheel. A higher Ferris wheel is different from a smaller Ferris wheel. The speed, you could go really fast and it might be very exciting. They don't usually go that fast, but you could. Or you could go very slow and then it's just like scenic. You get to the top and you get to look around a little bit, that kind of thing, right? So that's kind of what makes Ferris wheels different. And now that we've been talking about these sine and cosine functions, we can relate those better to the properties of these specific periodic functions. And so when we change the size of the wheel of the Ferris wheel, or when we speed it up, what we need to be able to do now is translate that into the terminology we use when we're talking about these periodic functions, sine and cosine. So before we do that, very quickly, again, this is the demo we saw before. This is the rider, this little black dot, and when I drag the slider, they're going to go to the top and then they're going to go back down, right? And so that's if you're standing on the side watching them, and we can go around twice in this case. Okay, if you're standing around off the side watching them, that's what it looks like. But if I want to graph the rider's height over time, okay, so the height goes up and then it goes back down. The rider's going in a circle, but time continues forward. So what actually happens is this dot, as time passes, is going to move to the right, and it's going to go for 2 minutes. But the height is going to be attached to the blue dot will be attached to the height of the rider. Okay, so it goes up, gets to the top. What's going to happen now? The blue dot is not going to circle back around because it's for time. It's going to keep moving forward, but the height is going to go back down to the bottom. And take a look at that. Isn't that a cosine graph? And it's reflected, but the rider started at the minimum. When it was at the top of the Ferris wheel, that's the maximum of the cosine. And just because of the way this one's been designed, we can fit 2 cycles in 2 minutes. So 1 cycle happened in 1 minute. And now we can see that the maximum height of the rider is equal to the maximum of the cosine curve. The minimum height of the rider is equal to the minimum of the cosine curve. And the period, the length of time that one cycle occurs, or one time around the wheel, is the period of the function, right? And so that's how we can model real-world situations with trigonometric functions, with trig graphs, okay? And then what happens if I change some of these properties? So with this applet, I can change them. So this slider that says speed tells me how many times I will go around the Ferris wheel in a minute. So right now it's set to 1. What if I set it to 2? So then in 1 minute, the rider will go around twice. And so that has changed the period of the graph. By speeding up the rider, right, speeding up the Ferris wheel, we've changed the period of the graph. And so that's one of the important details of periodic functions, of sine and cosine, is its period. And speeding up the Ferris wheel changes the period. The other thing I can do is I can add another graph, and I'm going to set these both to have a speed of 1. And now I can compare the two. So I can compare the original blue Ferris wheel that has a height of 32. I don't know if that's 32 meters, whatever it is. And I can compare it to a different one that has a height of 16. So this was the other property we talked about where the height of, or the size of the wheel, or how tall the wheel is probably an important property. And how does that change the graph? Well, it changes the maximum height. The minimum stayed the same in this case, but it changed the maximum height. But really what it's changing is the amplitude, right? So that's a change in amplitude. There might be some other details that are changing. The zero line's changing too, but that'll be a different part of the application. Okay, so that's kind of what this this applet is all about, showing how if we change the properties of the Ferris wheel, how does that change the properties of the graph? And I can do other things if I want. I could make, well, let's go back. I could make one even smaller and see what happens. And if it's really smaller, maybe it goes way faster. So in 1 minute, the small one's gone around 5 times, whereas the big one's only gone around once, and then 5 more times in 1 more minute, or 1 more time. You could do something like that. Or I can even decrease the speed, and instead of going around in 1 minute, it only gets halfway around in 1 minute and requires the other minute to do the other half. Right? And again, that's a change in period. And so what applications is all about is taking the details of the question and turning them into the properties of a periodic function so that we can do things like sketch it, write equations, and solve some simple problems in our case. We're really only going to look at 2 types. There is one that's slightly different in the homework, but it's very similar to a Ferris wheel question. But really we're looking at 2 types. You'll notice every question is either a Ferris wheel or question like our first example, or our second example is a little bit different, but most of the work that we're going to do is really about those 2 types. And you'll also notice that every time we're kind of asked to do the same 3 things. So we're going to sketch, we're going to write an equation, and then sometimes at least we're going to use our equation to solve a simple problem. And so that's nice because with these 2 application lessons, we're focusing on very specific details, very specific way of doing things. And so as you're practicing, it's kind of going to start to feel like the same every single time. Okay? So let's get into this first one. A Ferris wheel has a diameter of 10 meters. It makes 1 full revolution every 20 seconds. The center of the wheel is 7 meters above the ground. So usually I would try to ask the class to think about how they can label this diagram, but I'm going to try to get this lesson done quickly. If you want to pause and think about how we can label this Ferris wheel that we have here with these details, go for it. But if you just want to get to the actual completing this so you can figure out how to do it, you can just keep watching the video. You could probably figure out how to label the diameter in there because that's just the length of across the circle. So I'm actually going to label it off to the side over here. So this is 10 meters. Okay. And what does it mean when it says the center of the wheel is 7 meters above the ground? Well, that's this right here. That's the center of the wheel, 7 meters. Okay. Now we have to start making some deductions. The other thing I could do actually, and this is a good thing to do, is if it makes 1 full revolution every 20 seconds, so it goes all the way around in 20 seconds, how long would it take to go halfway around? And you'd be right if you guessed 10 seconds. So how long would it take to go a quarter of the way? And that's, again, half of 10, which is 5. And so on the other side, this is 15. Okay. So it might be helpful to label those times. Labeling this diagram is not a required part of the question. The sketch that I'm interested in is the one that's on the graph, on the grid. That's the one that has to get done. Drawing a picture of the Ferris wheel is not a requirement for these questions. So you only do it if it helps you. The last thing we need to realize is that if the diameter is 10, then the radius, which is half the diameter, the distance from the center to the outside edge, is 5. And the reason why this is important is because that radius goes everywhere in the circle. So it goes there, but it also goes, hold on, whoops, goes here, doesn't it? And that means that this distance from here to the top is also 5 meters. And that means I can figure out that this entire distance is 12 meters. Another way some people have looked at this is if the radius is 5 meters, this is 5 meters. And if that's 5 meters, this has to be 2, because this whole one is 7, and that means this is 2, and 2 plus 10 also gives me the 12. So, we've just thought about some different relationships, some different measurements. given what we were given from the question. Turns out all these numbers like 10, 5, 7, 12, turns out these are actually important properties of the graph. The ones that we considered, the 2 as well, that we considered when we were graphing. These are the actual numbers that we need, okay? So now that we've taken that, let's see how we can translate it onto our grid. Well, it says, sketch a graph relating time in seconds and height showing 2 forward rotations, and it says up here, assume the writer gets on at the lowest possible point, which kind of makes sense. That's usually where you would get on a Ferris wheel. So the lowest possible point is here, which is 2 meters, and so I can put a point at 2 meters. And if it takes 20 seconds to do 1 full revolution, a revolution is a full way around the Ferris wheel, so that means after 20 seconds, I'm going to be back to the bottom. And after another 20 seconds, I'll be back again to the bottom. So I can put all 3 of those points in. At 10 seconds, we saw here, we're at the max of the graph. Well, what's the max of the graph? Well, it's that 12 that we had. If at any point, if I am going too fast at any point you want to stop and think about it, just pause the video. You can rewind quickly to rehear what I said, or pause and think about it, pause it to copy down what I said. I know I am going fast. So back to it, half the way to 20 is 10, and that's at the maximum height, which is 12. So I'm going to go up to 10 and then up 2 more and put the max height 12. And again, at 30, I can put the max height 12. Now I can do one more thing. What would the height be at 5 and 15? Well, it would be that 7. Okay. So at 5, I'm at 7. At 15, I'm at 7. At 25, I'm at 7. And at 35, I'm at 7. Now, you don't need to always include these points. Not every scale is going to allow you to. They're useful because you can draw the curves a little bit better with them, but they are not required. Okay. The other thing about this, we're learning how to turn the details of the Ferris wheel into a graph, but you're also going to learn what's required to get full marks on a question on a test, and the things that I'm looking for and the things that your graph has to have. So I've got my points, and now I can draw my curves. And there you have it. And sure enough, it looks just like the ones we were looking at. It looks like a cosine curve. You need the maxes and mins as points in there. If you want to, you can do those middle points. Like I said, they help you draw a nicer curve, or at least I find they help me, but they are not absolutely required. But what we are going to do is label these numbers. So that one was 12 and that one was 2. And we don't usually have to label the x scale, it's already labeled, or the horizontal scale, it's already labeled. Last thing for a perfect graph is I have to label the axes. So this one was height of the rider in meters, and I'm going to call it h. I like to see you put that letter as well. That's going to come back in a minute. And this one is time in seconds, and I'm going to call it t. Okay, so there's our graph. Now, B says write an equation for your graph. So we talked about this before. To write the equation, I need the A, the K, the C, and the D. This is what I need in order to write the equation of a sine or a cosine curve. This is what we talked about all day yesterday, and that takes a big problem like writing an equation which sounds complicated, but it turns it into something simple that I can just do. And, oh, I forgot to do this one. This one was at 7, so that can be useful. These numbers can be useful for you in solving the problem as well. So everybody's going to approach this a little bit differently, but the idea is you start looking at your graph, either looking at this picture if you like, or your graph is maybe more likely, and figuring out what these values are. So I have my amplitude. I've got my middle, my 0 line, which is at 7, and I know the amplitude up to the max is 12. So the difference there is 5, and it's 5 up to the max and 5 down to the min, and indeed that is that 5-meter radius that we calculated over there. So that's going to be my A value, but it is also flipped. So this is actually going to be -5. And the D, the middle, that's that 7, that's that center point of the Ferris wheel. And we're starting at a minimum, which is where cosine starts. We're going to use cos, so we're going to call C 0. Finally, K, somebody asked today if the K value, if we calculate it the same way, absolutely you do. You always use that same formula. So it's 360 divided by the period. Well, what's the period? Well, the period is the length of time that to complete one full cycle, and that's 20 seconds, okay? So we do 360 divided by 20, and that should give us 18. So therefore, and now you don't have to do this, but I'm going to use function notation. So I'm going to use, say, h at t equals. You could just call it h, but you'll see why it's useful to do h at t later. H at t equals -5 cos 18t plus 7. Okay? So all that work we did on how to write equations is coming in handy now. And that's B done. We had to write the equation. We wrote it out. Some of you might like to write the 0 line off the side because that's what we were doing before, and turning that into the D value and the amplitude and turning that into the A value, and that's fine. You can do that too. C says, what is the rider's height after 8 seconds? So what this is saying is plug 8 into the formula. So it's going to be h at 8. Okay? And I plug it in, and I get -5 cos, hold on, 18 times 8 plus 7, and here's how I plug it into the calculator. -5 cos, you need those brackets, 18 times 8. You have to close that bracket, otherwise you're going to get a really wrong answer, plus 7. And this one's rounded. Sometimes you get rounded answers, sometimes we get nice answers. 11.0 meters. Does that make sense? At 8, around 11? Sure. Well, it looks good to me. Okay. It might not be perfect, but it's close enough for me, that's for sure. And it's nice to use your graph to just do a sort of visual check that the answer is reasonable. You know, if I got a negative answer here, if I got like 20, I would know that's wrong because it never goes up that far. Or even if I got 3 meters, I'd say, well, that doesn't really make sense. It should be up here somewhere, right? So it can maybe catch a mistake, and that might be brackets, or you missed a negative or something like that, if that happens. Okay, as long as your graph is right, it'll help. So that was one of the 2 applications that we're doing. That was the Ferris wheel question. The next question is a little bit different. Hopefully this is something you know something about. It's about tides, and the tides is actually caused by the gravitational pull of the moon, and what it does is throughout the day, the water level of different areas of the ocean change. So it can change up to a lot within a short amount of time. Okay, so at one point of the day, it's going to be deeper, and at one point of the day, it's going to be shallower. And that's what this question is all about. Okay, so in one area of the Bay of Fundy, the tides cause the water level to rise to a maximum of 13 meters and lower to a minimum of 7 meters. One cycle is completed approximately every 12 hours. Sketch a graph of the water level starting at high tide for 24 hours. Now here's the first thing I'm going to do is point out a common mistake. It says starting at high tide. It says high tide is 13, so I'm going to start by putting a point at 13. Now what people do is they say, oh, one cycle is completed every 12 hours, so it goes to 7 at 12, but this is wrong. That's not a cycle. That's going from the max to a min. A cycle is when you repeat and you end up in the same spot. So after 12 hours, I should be back up at 13. We don't have a separate diagram for this one. We just have to put it straight into the graph. So that's what a cycle means. That's a common mistake. Be careful. Even though we've talked about it, it's a mistake that you might make. Now, next, what we can do is now we can find out where does that 7 go? Well, if I do one full cycle in 12 hours, then half a cycle will be in 6 hours, and so that's where that goes. And so there's my 7, and there's my 12, okay? And so in this case, where's my middle going to be? My middle, this should be 13. That's why it's not working out. Not 12. 13. That's better. So I have a distance of 6 between 7 and 13, and that's 3 each. So we see this number 10. It happens to be on the scale. I go 3 down to 7 and 3 up to 13. So my middle is indeed 10. And if you want, you can add those points, and that'll happen after 3 hours. And then 3 more hours, I'm at the minimum, and then 3 more hours, I'll be in the middle, and then 3 more hours, I'm at the maximum. Now the question says to do 24 hours, so I've got to go all the way around again. So that looks like 3 right there and there. Okay, and now we can draw our graph. All right, so that's pretty good. I think that's done, except for our labels, and you could call this height. I like to call it depth, meters, but it doesn't matter if you call it height. It is a height of the water. I'm fine with that, and T. Okay, so a little bit different, and some common mistakes that can happen in there. We talked about them, so keep those in mind. But the nice thing is it gives you the max. This question does typically give you the max and the min straight out, so it might even be a little bit easier once you pick up on what's going on. B is writing an equation for the graph. Again, for the equation, I need the A, the K, the C, and the D. Okay, and again, we're going to do cosine. Cosine starts at the max, so C is 0. A is the amplitude. We've already talked about that. That's that distance up from the middle. That's why it's nice. That's another reason why it's nice to find the middle. If you've already thought about all these things when you do the graph, then coming up with the equation should be fairly straightforward. So that's 3, and in this case it's positive because we're starting at the max. So my amplitude is 3, so my A value is 3, and D is that middle value, in this case of 10. K is 360 divided by the period. Period is 12 in this case. 360 divided by 12, again, you know, always be checking these on your calculator, but this one gives us 30. So therefore D at T equals 3 cos 30T plus 10. You'll notice, here's a tip, the C is basically always going to be 0. As long as we go with cos, and for us we're only doing a couple of types of applications. There are certainly other applications where this wouldn't be the case, other kinds of questions where it might not be the case, but for us, we can always get away with using cosine, which means we start at a max, or a min, which means our phase shift can just be 0, we'll have none, and the C value will be 0. So our equations are going to be similar. And again, as I said in the opening, if you're doing the practice and following along, you're going to notice there's a lot of repetition here. The questions are very similar. The numbers are different. Once in a while, in particular, in this question, the Ferris wheel question, they might give you the numbers in a bit of a different way. They might give you the radius instead of the diameter, that kind of thing. Very small changes, but they do sometimes do that. Less so with the tied questions. But otherwise, the questions are very similar every single time. Last question. Now, if you printed this out earlier, I did change this question, so you might have had a C and a D, and they're different, but we're not gonna worry about those right now. So you can change your question C to how deep is the water after 7 hours? This is actually basically, it's worded differently, but it's basically the same question as question D from before, if you saw that in the lesson previously. So again, I just sub it in. And punch this into my calculator. 3 cos, my calculator opens a bracket, so I'm good for that. 30 times 7, I have to close that bracket, plus 10 equals, and if you get a weird answer like that, you hit the S to D button. Most of you probably know that at this point, 7.4 meters. Okay, so that's it. Those are the 2 types we're looking at. The practice only has 2 more types. You will probably want to print it out because you want to be doing it on that grid to practice doing it on a grid. The test will have the next lesson, which you may have already looked at if you went ahead. You'll notice that there is no grid. Okay, so let me just get rid of this for a second so that we can see it. It's just a blank grid. It's not labeled, nothing on it. So the next lesson will tell you about what I need to see for those kinds of sketches. And there'll be one question like this on the test with no grid, and one question like this on the test that has a grid, so you need to know how to do both. They're not all that different. Again, when you do it, I want to see these labels, these labels, these labels as well for the max and the min. Not only do I like to see it, but it will help you when you're coming up with the equation and make sure that you're getting your points and everything in the right spot. Okay, and then we usually come up with the equation, and then we usually use the equation to find at least one value to solve a simple problem. That's kind of how these things play out for us. Okay, that was fairly quick, but I hope that was okay. As always, let me know if you have any questions. I'll upload this right now, and hopefully you'll find it and you can take a look at it. Good luck.